Okay. A couple things I want to mention before we start diving into stuff here. First thing is that we have a quiz today, so you can take it anytime between 9 a.m. or I'm sorry, 10 a.m. and 9 p.m. It'll be open all day for that, just like we have been doing. So I think that's been working out really nicely. And the other thing I want to mention is that if you scroll down on the My Open Math page there, in our 7.2 folder under the Unit 2, you'll see that I added 3 examples there that I just didn't get to cover on a Wednesday. I went ahead and finished out the lecture there. It's just 3 extra examples. You can see which examples they are from the lecture notes. So if you're fairly confident that with that material, you probably don't have to watch those lectures. Although, to be honest with you, example 11, I go into a little more detail and pull together. It's more than just an example, I'll just say. I pulled together a lot of the techniques that we're learning in that trigonometric integrals section and summarize that. So maybe example 11 is a good one to watch. Anyhow, another thing I want to mention is that there was, if you've already started, I think it's, well, let me just double check. I think it's assignment 7.2, but let me just double check. Yeah, if you've already started assignment 7.2, the last question had a coding error. I just just let me know this morning. This was supposed to have a function name on it, and so it didn't in the originally, but I just fixed it. So just know that the last problem on the homework, it now has been fixed. Sorry about that. That was my fault. That's all I need to say about that stuff. So let's go ahead and we're going to start today into, waiting for this to catch up to me. Interesting. There we go. We're going to start into trig subs, which is different than trig integrals. Just slightly different, not a huge amount of difference, but enough of a difference that it's probably good to have a conversation about it. So I like to summarize as we move through this material because it is, there are going to be a lot, it's going to feel like a lot of techniques after a while. So let's go ahead and just talk about our tactics so far. The very first tactic you ever learned was in Calc 1. It was just direct integration. So if you had, let's say, the integral of secant squared, that's tangent, that type of thing. Then the next one, and I give some advice here, right? Keep an eye out for simple algebraic manipulations or trigonometric identities in the integrand, as performing them often leads to this form, a direct integration. Then a U sub was the next thing that you learned, also from Calc 1. And this tactic is useful in many instances, especially if there are 2 functions in the integrand and one is pretty much the derivative of the other. That is a really good clue that you're going to use U substitution. Or if you have a composition of functions in the integrand, then again, you're going to tackle that using a U sub. The advice here is to convert back to the original variable in the end if you're doing indefinite integrals, or change the limits of integration for definite integrals. That's always a good piece of advice, or often is a good piece of advice, actually. There are some exceptions. There's always exceptions to these rules. And then the one we just went through are trig integrals, which is misspelled there. Sorry about that. I'll have to fix that. I will right now. Trig integrals. Well, that looks worse, doesn't it? All right. So anyhow, trig integrals. So these are like glorified U substitutions, basically. You have sine to the 6th power times cosine in your integrand. Well, then let U equal sine. It steals away that power, that odd power of cosine. So that's what we've been going through. And all we're doing is just some U is equal to some trig functions. These tend to be somewhat obvious. They have the form of sine raised to the nth power times cosine raised to the nth power, or secant to the nth times tangent to the nth. Just letting you know, if it's secant tangent, when I say that, I really am also saying cosecant cotangent. So just letting you know there's a sister function to that. Anyhow, the advice here is just remember to try a substitution that forces the other trigonometric function to end with even powers after the change from dx to du. Now, again, everything I'm saying is a rule of thumb. It's very breakable. That's why integration is considered a very heuristic method, which means that it just takes a lot of practice to figure out kind of the best tactics. Anyhow, once you get to even powers, then you just use trigonometric Pythagorean identities. If the powers on m and n, at least for the sine times the cosine, start as even, in other words, if they're both even there, so let's pretend for a second that this is like cosine, or I'm sorry, sine to the 6th and cosine to the 8th, then you're in the worst possible case scenario, because when you have even powers like that on sine and cosine multiplying, then you have to do power reduction formulas, and that can be an absolute mess. So giving you a heads up, the worst case that I would give you on a quiz, let's just say, would be a 2nd and a 4th power or something like that, because it can get really, really nasty if you go through and get high powers. But you use half angle identities, or a lot of people know them as the power reduction formulas, and they just kind of look like this. There's one for sine squared as well. And like I say there, this can get messy if the powers are large. Additionally, these types of integrals are common targets for extra u substitutions and by parts methods. So be aware of that. That can happen, that you do some work and you manipulate. Let's say you have sine to a power times cosine to an odd power. So you let u equal sine, it steals off the odd power of the cosine. You might end up having a by parts after that, or another u substitution that you have to do, whatever it may be. Finally, if the arguments in the trig functions, if they're not the same, for example, this stuff right here, where they're different angular speeds, then you must resort to using the somewhat obscure product of sum formulas from trig. I would provide those if necessary on an exam or quiz. These actually make it very easy to work with the functions because of the fact that it's a simple formula. If I provide you with it, right? It's just that they're very obscure. A lot of people will forget them, myself included. So anyhow, there are some integrals which require non-obvious substitutions. For example, cosine cubed, that type of integral. Notice it's an odd power on the cosine. So this one, even though you don't see it there, I would let u equal the sine. So it steals away that odd power of cosine, and then you do the Pythagorean identity. And then we learned integration by parts. And actually, we learned integration by parts prior to learning the trigonometric integrals. It's just that because I think of trig integrals as specialized u subs, I lump them into a conversation about u substitution. So that's why it's kind of right after u subs. But integration by parts, that's a really powerful technique. It's almost the last technique I go for, though, to be honest with you. Typically, this is a great method if the integrand is a product of different types of functions. Some advice here. I find it best to look at the ugliest part of the integrand that you can integrate and let this be dv. Another good tactic is to choose u to be the function whose derivative is less complicated or a different form than the original function. So in other words, if you have a natural log, I'd probably let u equal the natural logarithm because, well, its derivative changes forms. Finally, many integrals can be done using this method that do not match the product of different functions rule. For example, the tangent inverse, you can integrate that using by parts. So don't get married to this idea that it has to be a product of two different functions. So again, every rule with integration is very much a rule, just a rule of thumb. There's a lot of ways to break the rules. But as we move forward, I build on this list, and I also start compacting it a little bit so it fits on a single page. But by the time we get through all the integration techniques, we'll have a nice list and a list of tactics and how to tackle things. But today, we're going to focus on probably what most students think is their favorite method, or most students prefer as their favorite method. So for our next integration technique, we again look back to substitutions. So again, we're just doing more substitutions, but these are what are hyper specialized substitutions is what I would call them. This time we focus solely on the Pythagorean identities from trig. So let's start with a simple comparison. Let's evaluate each of these if possible. Notice they're very similar to each other. The top one is just x over the square root of x squared minus 16. The bottom one is 1 over x squared times the square root of x squared minus 16. I hope you can realize there is a very simple way to tackle the top one. You should always think simply first. So what is probably the best thing to do with that first integral? Anyone? Bueller? Get rid of the x somehow. It's definitely a good idea. This is okay. So I have a lot of good suggestions there, and they all kind of center around sort of the same thing. Get rid of the x somehow, right? That's a great idea. I'd like to get rid of that x. And the way we can get rid of that x is maybe through a u substitution, through letting u equal that, which often, by the way, in this situation, we'll end up with drawing a triangle, just to let you know that does actually end up happening in the long run. But always try to think simply, look through our tactics that we've learned so far, and always start with, do I know the antiderivative offhand, which you don't, or actually you might. But the next tactic you learned was a u sub. And if you look at that denominator, specifically this part of the denominator, you could easily see that if you let u equal x squared minus 16, its derivative is sort of right there. So I will write that in blue. Let u equal x squared minus 16, then du will steal away a 2x dx. Notice I don't have a 2x dx to steal away. I just have an x dx, but that's still okay. I can just modify this by saying that's the same thing as 1/2 du is equal to x dx. Very, very nice substitution. And here's where I really am going to showcase a very nice alternate substitution in a moment. But let's go ahead and finish this problem out very quickly. So our integral becomes, let's see, I'm going to trade out that dx for a du times 1/2. The x dx got stolen away for that 1/2 du, so that's no longer there. And downstairs, I have the square root of u. And now I can finish this out very quickly, because this is just going to be 1/2 integral of u to the negative 1/2 power du. As I tell my students in my pre-calculus class and Calc 1, well, really it's pre-calc and trig that I tell my students, we let go of working with radicals once you reach calculus, because most of calculus works better with rational exponents. We're going to add 1 to that exponent, so it becomes a u to the 1/2, and multiply by the reciprocal of that new exponent. Don't forget the plus c, and don't forget you're going to trade this out for the world of x's. So u was this x squared minus 16, so this is going to be the square root of x squared minus 16, and then plus c. That's the antiderivative of x over the square root of x squared minus 16. Now, before I step away from that initial example, which is just a u sub, so there's nothing special, we didn't learn anything new there, but I do want to showcase an alternative way to do the u sub, and it's called a radical substitution. And it's good to learn it now than to wait until section 7.4, which is where it's actually introduced. It's such a simple alternative to the u sub we just did, it's worthwhile to talk about. So I'm going to go ahead and draw this in a different color here. And I'll say another, how do I want to say this? Another u sub style, which is called radical substitution. It's just another way to do a substitution, that's all, okay? But when you're facing this initial integral, and in fact, I'll write it down below so you know which one I'm talking about, the integral of x over the square root of x squared minus 16 dx. When you're facing that integral and you know you want to do a u sub, it's often better to do the u sub for the actual square root of x squared minus 16. It's just tactically cleaner. So if you let u equal the square root of x squared minus 16. Now, a lot of people look at this and say, but then I have to take a derivative of a square root. No, actually you don't. Square both sides. If you square both sides, you get u squared is equal to x squared minus 16. And you can take the derivative implicitly. The derivative of the left-hand side is 2u, then du. Well, it's technically called the differential of the left-hand side is 2u du. The differential of the right-hand side is 2x dx. The 2's cancel. And I get that wherever I see an x dx in that integral, I get to trade it out for a u du. And wherever I see a square root of x squared minus 16, I can trade that out for a u. So this will become the integral x dx gets traded out for a u du. And that denominator, the square root of x squared minus 16, gets traded out for a u. It's a really cool way to do a substitution. It's almost always an option. And the integral of 1 is going to be u plus c. And remember, u was equal to the square root of x squared minus 16. A really, really swift, clean substitution. You may have already learned that style of substitution in your Calc 1 course. I only do a single or example, maybe 2 examples of something like that in Calc 1, mainly because it's usually left for Calc 2. But it's a simple change up from a regular u substitution, like, oh, I'm going to let u equal the interior or the radicand, x squared minus 16. No, you can actually let it be the entire radical, just square both sides and clean it up. Anyhow, that's kind of a neat way to do it. But now let's take a look at the second integral. The integral of 1 over x squared root x squared minus 16 dx. And this one is not as easy. Just a simple change up in form, but the problem here is that if you were to allow u to equal the x squared minus 16, remember, du would steal away x dx, essentially. And we don't have an x dx to steal away. We have a 1 dx. So the u substitution, u equals, even if I did a radical substitution, let's suppose I did that. The radical substitution, u equals x squared minus 16, which leads to u squared equaling x squared minus 16, which leads to 2u du is equal to 2x dx, which leads to u du equals x dx. Well, it's not a great substitution because, again, our original integral does not have an x dx. It only has a dx. So what I need to do is divide both sides by x on this piece right here. And I'll say, well, wherever I have a dx, I'll trade it out for a u du over x. But when you do this substitution, so let's go ahead and see what happens. The dx will be traded out for a u du over x. However, that denominator still has an x squared, and it has the square root of x squared minus 16, which we call u. Which, when you look at this, you think, well, that's not too terrible, because the u's will cancel, and we have a du over x cubed. And remember, you can't work with this because it's a mixture of variables, but maybe there's a relationship between x and u, and there is. This guy well, either of these guys right here actually would work. However, I need to get it to be an x cubed, not an x squared, which makes it really, really ugly. That'd be a u squared minus 16 is equal to x squared, and then you would raise both sides to the 3/2 power to get an x cubed. It is a plus. Thank you. Oop, there we go. You raise both sides to 3/2 power so that the right-hand side there becomes an x cubed. So now I know what x cubed is in terms of u's, and it still leads us down the road to a terrible integral. And in fact, has not gotten better, but almost worse in complexity. So the question is, how in the world do you integrate something like this? Well, this leads to a new method. So each time that we run into an integral that seems impossible to integrate doing u subs by parts or anything like that, we have to invent a new method. So the new method we're going to talk about here is the trig substitution method. We're going to build the concept right now. And the way I like to build this concept is just to remind you of your Pythagorean identities in trigonometry. So recall, and we wrote them down last time as well, but it's nice to see this. Recall that the cosine squared of theta plus the sine squared of theta is equal to 1. Pretty simple statement, right? Well, I'm going to rewrite that and solve for one of those. And I'm actually going to solve for the cosine squared. It's kind of a tradition to do that. So cosine squared is equal to, zoom in a little bit so my ink is not so terrible, 1 minus the sine squared of theta. And let's take a look at a different Pythagorean identity. How about this one? The tangent squared of theta plus 1 is equal to the secant squared of theta. Well, this identity right here actually leads to itself. So I'm going to highlight the ones I want to focus in on here. It leads to itself, but also you can manipulate it slightly and subtract 1 from both sides, and you get that tan squared of theta is the same thing as secant squared of theta minus 1. These three identities, technically there's only 2 there, but those 3 versions are the ones we're going to focus in on. Because what we're going to look at is when you have a sum or a difference of squares in your integral, you're going to trade them out for trig functions. So the idea is this. The idea. Given an integrand involving, I'll write it this way, some type of variable squared minus a number, possibly squared, or a number squared minus a variable squared, or a variable squared plus a number squared. We're going to let that variable squared be a version of sine, tangent, or secant. For example, variable, or I should probably say off to the left here, happy face is a variable. K is a constant. Just so that's clear for you guys. Okay, so imagine somebody comes in the room and they say, I've got this integral. And the integral is, let's just pretend the integral is 1 over x squared times the square root of x squared minus 16. Oh, let's just pretend, right? Notice that difference of squares right here. It's a variable squared minus some number squared. Now think about those 3 trig identities that I highlighted. I'm looking for a variable squared minus a number. This is a number minus a variable. This is a variable minus a number. So in the variable squared minus number squared case, I'm going to let that variable be some version of the secant. Because then I get secant squared minus basically 1. I'll show you how we can force that in a moment. If the integrand had, instead of this x squared minus 16, what if it was 1 over x squared times the square root of 16 minus x squared? In other words, it's a number minus a variable squared. Again, that one should be somewhat obvious. 1 minus sine squared. That's really what I see. When I see 16 minus x squared, I actually see 1 minus sine squared because it's very close to that format. It may not look that close to you, but it is very close. I can make it into that if I want to. So when I have a constant minus a variable expression being squared, we're going to let that variable expression be approximately, and I should say that here too, be approximately like the sine. It's not going to be exactly, but we'll modify it. So if you do that, it'll be like a 1 minus sine squared, sort of. Finally, somebody comes in and they say, no, sorry, I miswrote that integral. It's supposed to be the integral of 1 over x squared times the square root of x squared plus 16 squared, or plus 16, sorry. Well, in that case, again, I think about trig identities. Tangent squared plus 1. That has the same form as tangent squared plus 1. So we're going to let theta, or sorry, happy face, roughly equal tangent of theta. Because again, tangent squared plus 1 can be traded out eventually for a single statement. That's the whole idea. We're going to trade out those sums and differences of squares for single statements. So if it's a sum of a variable squared plus another number, I can trade that out eventually just for a secant squared. If, on the other hand, it was some number minus a variable statement squared, if I let that variable statement roughly be the sine, I can eventually trade it out for the cosine squared. And no, it doesn't have to always be inside a square root. That's generally the traditional introduction to the topic, but actually it does not need to be in the square root, and it does not need to be in a denominator. It could be anywhere. It's an option no matter what. How's that? Whenever you see the sum or a difference of a square, you know that doing what we're doing right now, which is called a trig sub, because you're substituting in trig functions, that is going to be an option. Do we have to memorize? Yes, you do have to memorize these. yeah. You'll trust me, you'll work with them enough that it will just become part of your memory very quickly. Now, I was going to derive some of the domain restrictions here, but I think it's probably best to just see this in action first. And if we have time, I'll derive them. If not, I'll make a video for it, just deriving. We basically derived it, honestly, but deriving why there's not an absolute value in the end. Don't worry about that statement. I'll explain it when we get there. So the next page, which says, but why does this work right here? We're going to ignore that right now. I'm going to just go through and showcase how to use this stuff. But this is the how-to. Given an integral with a sum or a difference of squares in the integrand, where a simple u substitution will not work, and asked to evaluate, what do? Well, if the integrand contains a difference of squares of the form a squared minus x squared, let x equal a sine of theta. Now you may say, wait, I thought you said sine of theta. I did, but I'd like this to eventually become a 1 minus sine squared. So if you let x equal a sine of theta, then x squared is a squared sine squared of theta, and you can factor out an a squared, and now look what you get. And it's very beautiful, because that is a squared cosine squared. It simplifies the statement down significantly, and that's what you want to do. Always in mathematics, you want to simplify things down if you can. If, on the other hand, you have a difference of squares, but it's a variable squared, like x squared minus a squared, then let x equal the secant. And likewise, if it's a sum of squares, then let x equal a tangent. Again, we'll see this in action. Now, one thing about the secant substitution, I give you the domain restriction. Again, I think I'm just going to create a video for that later on today, so that you could watch that at your own leisure. Most people, it's not going to make much of a difference whether they watch it or not, but some people are very curious about the theoretical implications of it. So I'll make a video for that. It's not going to be worthwhile for us in this discussion today. All right. Let me take a drink before I start into this example. All right, let's go back and do this example right here. Evaluate the integral of 1 over x squared times the square root of x squared minus 16. Now, we already have seen this integral, and we tried to do a u substitution. It didn't work out for us. So instead, you look at the form of this and you say, man, you know what that's like? That's like a secant squared minus 1, sort of. It's not exactly, obviously, right? Because that's not a 1, that's a 16. So I'd like that x squared to eventually be a 16 secant squared. So we're going to let x equal 4 secant of theta. If you let x equal 4 secant of theta, then x squared is going to be a 16 secant squared of theta. And whenever you do a substitution in Calc 2, you are substituting because you're changing the integration, the variable of integration. So you have to trade out your dx here for d theta. So let's go ahead and figure out what dx is. And this is probably the most beautiful thing about a trig substitution like this, is you will always directly find out what dx is. For example, x equals 4 secant of theta means that dx is directly substituted out for 4 secant tangent. 4 secant of theta, tangent of theta, and then d theta. Does it work if there's a coefficient in front of x initially? Yep, it sure does. And we'll see examples like that. Yeah. So every one of those questions you guys are asking, I have examples for. So we will go through and see them. So it's perfect. Good that you're on top of that. All right, so if I make that substitution, that x is equal to 4 secant of theta, so therefore dx is equal to 4 secant tangent of d theta, then I will go ahead and take this original integral, and I'll say, oh, that's the integral of dx will be traded out for a 4 secant of theta, tangent of theta, d theta. You do get a lot of trig functions when you use this. However, it cleans up beautifully. Okay. Downstairs, we have an x squared. Well, we know what x squared is. It's 16 times secant squared of theta. And then we have the square root of x squared minus 16. That's the square root of 16 secant squared of theta minus 16. Now, that may look ugly to you, but I promise it cleans up, like I said, beautifully. I'm going to move the constants out front. Obviously, 4 goes into 16 downstairs, so that's just a 1/4. The secant, I was going to say the 16, the secant here will cancel. It was supposed to be red. The secant there will cancel with 1 power secant there. So I'll just write that as a power of secant downstairs. So we're left with a tangent of theta, d theta, upstairs. And we still have this square root of 16 secant squared minus 16. And you know you can factor out that 16 and take its square root. So I'm going to do that. I'm going to put that 4 right here. And we're left with the square root of 6 secant. I'm going to say 16 over and over again. Secant squared theta minus 1. And notice that's a trig identity. Secant squared of theta minus 1 is tangent squared. That's why we did that substitution. All of these substitutions are done for a reason, to squeeze them down to their Pythagorean identity. So this becomes a 1/16 integral tangent of theta d theta all over secant of theta times the square root of tangent of theta squared. Now, here's where a little aside conversation happens. This is what I said I might just put in a different video. So I'll say it out loud. I'll prove it in a different video. But most of algebra, you should adhere to the statement that the square root of something squared is the absolute value of that something. Okay, it is very true. The square root of x squared is the absolute value of x. It's not x, it's the absolute value of x. So therefore, it should be the case the square root of tangent squared of theta should be the absolute value of the tangent. However, there's something very special about our substitution. Our substitution for for x equals 4 secant, that means that theta, the angle itself, is restricted. Because when we make this type of substitution, it's based upon the inverse trig function. And I'm not going to go into too much detail other than this, just say that these angles are actually going to be somewhat restricted. If I hop back 2 pages, or maybe it was 1 page, sorry about that. If I hop back 1 page, when I make the secant substitution, I'm specifically stating, by the way, our angle is only going to be in either quadrant 1 or 3. And again, I'll make a separate video to justify a lot of this. It's very deep to get into in a single lecture. So, but anyway, that angle is either in quadrants 1 or 3. The reason why I want to have those 2 quadrants for my angles, tangent in quadrants 1 and quadrants 3, it's already positive. I don't need those absolute values. Kabam. And that same argument is works for all of them. And again, I will make a video for that so that I spend a little more time than that. Because normally if it's in a classroom, I've done it before, but in a classroom, that's like a 45-minute conversation. I don't want to burn 45 minutes for that. So for now, just know that whenever you do a trig sub, the square root of that trig function squared will actually be just the trig function. In other words, you don't have to worry about the absolute value. And again, I'll make the video justifying that. So in this case, you can see that our original integral, 1 over the x squared root x squared minus 16, through a simple, well, I'll say through not a simple, but through a substitution, simplifies all the way down to 1/16. The tangents cancel, and 1 over secant is the cotangent. Or sorry, cosine. Jeez. Don't listen to me today. 1 over secant is the cosine. And I know the antiderivative of the cosine is the sine. But we did not start in the world of thetas. We started in the world of x. And this is where I am gluing in what Alyssa said, which is draw a triangle, because that's exactly how you're going to finish this out. You're going to use your trigonometry. So when you go to finish this, you note if x equals 4 secant of theta, then x over 4 is equal to the secant of theta. If you don't like to deal with secants, that's fine. Take the reciprocal. That just implies 4 over x is equal to the cosine of theta. I personally like to not deal with the reciprocal functions, so I tend to just deal with cosines and stuff like that. Now draw a triangle. Here's theta. Yes, I know that I'm restricting this triangle to look like it's in quadrant 1. We could talk about that if you want, but it's either in quadrants 1 or quadrants 3, which I'm reserving for the video. So let's see. Cosine is adjacent over hypotenuse. And therefore, the other leg is going to be the square root of hypotenuse squared minus adjacent squared by the Pythagorean theorem. And just looking at that triangle, I could tell you what the sine of theta is. It's opposite over hypotenuse, square root of x squared minus 16 over x. And that's what I will write in here. Equals square root of x squared minus 16 over 16 x plus c. So the steps to doing a trig sub is, first of all, to identify what you're going to substitute. So the first step I always go through, I'll just write it this way. 1, identify the type of trig sub. Okay, so in this case, it's a difference of squares, and it's something squared minus 1. I know it's not a 1, but that's how I visualize it. Always try to think of it that way. So once you do that, you then let x equal whatever the trig function is that you're going to sub in for, and find and compute, I'll say, dx. Sub in all that stuff, simplify, and use trig identities, and use technically Pythagorean identities, but whatever. And then once you're done with that, you should be able to integrate. So I'll just write integrate. And at the end, sub back to x by drawing a triangle for your original sub. So if I read through that, identify the type of trig substitution. Oh, it's like an x squared minus 1, or in other words, a secant squared minus 1. So my substitution is x equals secant, sort of. Obviously, if I just put secant here, that would be a secant squared minus 16. I can't do anything with that. So I need to make it 4 times secant, because then when I square it, it becomes a 16 secant squared, and I can factor out that 16. Okay, so I identified my substitution. I then performed the substitution and found dx. I then substitute that stuff into the integral, and I spend quite a bit of time simplifying. I did use a a Pythagorean identity. I took the square root, I canceled, I integrated, and then finally, at the very end, I subbed back into x by drawing a triangle for the original substitution. So I go back to the original sub, this guy right here. I note that x over 4 is secant. And by the way, there was a question Avi asked. Avi, I'm answering your question literally right now. So x over 4 is the secant, which just means 4 over x is the cosine. And I draw a triangle, right? If I know the cosine of theta is 4 over x, then the adjacent side to my triangle is 4, and the hypotenuse is x. And now I can use Pythagorean theorem to find that missing leg. And now I look at what I'm going for. I'm going for the sine of theta. So I just say, well, what is the sine of theta? Well, it's opposite over hypotenuse. Root x squared minus 16 over x. And bam, we're done. That's a really, really, really cool method. I will warn you, though, or I want to warn you, that once you learn this method, you'll want to use it for every single integral. Don't. I mean, you could see, like, actually the very first example in this lecture was this guy right here. And it would be silly to do a trig sub on this. A u sub worked, right? Let u equal x squared minus 16, or the square root of x squared minus 16, and you're almost done, right? So don't just knee jerk to saying I have a difference of squares, so therefore I'm always going to use a trig sub. No, that's not true. You sometimes use it, and often you'll just try to find something simpler to work with. All right, and I'm keeping my eye on the chat. Just if you do have questions, I will answer them as they come up, or if I know that I'm going to answer them in a moment, I'll let you know that I'm coming up on the answer. So let's take a look at this guy. Evaluate this integral. Again, I would highly recommend investigating possibly a u sub first. In this case, a u sub is not going to work, but you could try it. There's nothing wrong with trying it. So tactics, u sub. If you try a u sub here, And there's nothing wrong, again, with just quickly trying to u sub. So if I try u equals, I'm going to actually do a radical substitution here. U equals the square root of 25x squared minus 4. That means that u squared is 25x squared minus 4. And so that 2u du is equal to 50x dx. Divide both sides by 50x. We'll get u du over 25x is equal to dx. The reason why I divided by x as well is because my integral does not have an x times a dx. It has a dx divided by x. So I don't have an x times dx available. So I just moved everything over to the other side. Now, if you were to try to integrate that, or at least do the substituting in, you would have the integral of u, because u is the square root, and dx gets stolen out for another u, du over 25x, and then you still have that x downstairs. Actually, this is a decent substitution. Now I'm looking at it, right? We have that x downstairs, and we have the 25x. So this would be the integral of u squared du. I'll move the 1/25 out front, over x squared. Now, you might be able to do something with this because I can solve that equation for x squared. It's a bit ugly, but you could totally do it. You could say, oh, that's u squared minus 4 divided by 25 is equal to x squared. And you can make that substitution. That's kind of neat. In fact, I probably would write it this way. 25x squared is equal to u squared minus 4, or plus 4. Geez, me and my pluses and minuses. Plus 4. So if you do that substitution, the u substitution that we chose, then you know that 25x squared is the same thing as u squared plus 4. Well, here is a 25x squared. So I can trade that 25x squared out for a u squared plus 4. However, when you do that, u squared over u squared plus 4 du, you still have a little bit of work. Not too much, though. In fact, let's just finish this one out, and then I'll see how it would have worked had we done a trig sub. This, to integrate, there's two different ways you can do this. You can either do long division, or you could do a trig. I love this problem for so many reasons, so please pay attention. This is a really good problem. So let's go ahead and split this into two possibilities. 1 or 2. The first one, I'm just going to show that trig that I showed before, which is we have a u squared over u squared plus 4 du. You can always add and subtract a number to your integrand because you're just basically adding 0 when you do that. So that's a very viable tactic. You totally do that. And when you do that, you get the integral u squared plus 4 over u squared plus 4 minus 4 over u squared plus 4, and then du. Now that first term is just a 1. The second term, well, that's still 4 over u squared plus 4. There's not much you can do with that. That second term, though, should be reminiscent of a very powerful integrand, which is 1 over 1 plus x squared. So let me go ahead and run this integral a little bit. The antiderivative of 1 is just u. And I am going to leave this 4 in the numerator because I want to showcase something here. This usually comes from experience working with integrals, but you can totally divide both numerator and denominator by 4. If I do that, I get 1 over u squared over 4 plus 1 du. The reason why I did that is because I want to take advantage of an integral that we know. We know the integral of 1 over 1 plus x squared dx. We know that's tan inverse of x. Well, technically plus c. We know that. And we're very close to that when we have 1 over 1 plus something squared. All I need to do is rewrite that something squared in a prettier form. So I'm going to rewrite it as, well, we have that u hanging out front. We're going to rewrite that as the integral of 1 over 1 plus, and instead of u squared over 4, I'm going to write that as u over 2 being squared. And now I have the antiderivative at hand. This is going to be u minus this form right here, 1 over 1 plus variable squared, is the tan inverse of that variable. However, because that variable is being divided by 2, the antiderivative will be multiplied by 2. And then don't forget plus c. So that little trick I taught basically back on day 1 about when you have, I think we were dealing with natural logs at the time, 1 over 2x plus 1 or something like that, that returns the natural log of its argument, but because its argument is being multiplied by 2, the antiderivative is being divided by 2. You multiply by the reciprocal of that coefficient. Well, same thing here. Since the argument is being divided by 2, we multiply the antiderivative by 2. That little trick is incredibly powerful. Now, in the end here, you would have to go back and figure out, what did I let u equal from the get-go? Oh, yeah. U from the get-go, way back up here, was the square root of 25x squared minus 4. So let me go ahead and just plug that in over here. This is the square root of 25x squared minus 4 minus twice the tan inverse of the square root of 25x squared minus 4 all over 2 and then plus c. That's a very long road to build to get to an answer, but the reality is it works. So a u substitution does work here. The other way that I wanted to showcase with the u sub, I haven't done a trig sub yet, but if you're really married to the idea of wanting to do a u sub all the time, another way you could integrate this right here, rather than using the trick of adding 4 and subtracting 4, is to use long division. You could say, okay, well, since I know, and I'm going to do this in blue, since I know that I'm going to integrate u squared over u squared plus 4, that is actually what we would call an improper integral or an improper fraction. We would like the power of the numerator here to be less than the power of the denominator in the long run. So you do that by performing long division. U squared plus 4 goes into u squared plus 0u plus 0. Well, u squared goes into u squared once. Multiply back through. U squared, 1 times 4 is 4. Do a little subtraction, just like you did back in arithmetic. U squared minus u squared is gone. 0u minus 0u, that's gone. 0 minus 4 is a negative 4. And now I know negative 4 is the remainder, and that integral becomes the integral of the quotient 1 minus 3 or plus the remainder, but the remainder is negative 4 over the divisor. Notice this is exactly where we were right here. I had to find it. Okay, so long division can be really powerful, and a lot of people prefer it, but the trick can be faster at times as well. So anyhow, from this point forward, it's the same mathematics. So just look up there for the rest of that. Now that's if you're married to the idea of using a u substitution. But just letting you know, a u substitution is not always the best. If it works, it works. It's awesome. But let's see what would have happened had we done a trig sub. And this goes back to what Veronica was asking, which is, can we only do this if we have 1 as the coefficient? And the answer was no, you can actually have anything as your coefficient. So let's see how that works. Now, if you take a look at this, we have to decide what type of substitution we're going to make here. This looks very much like a something squared minus 1. That's what it looks like to me. I forget about the numbers. I just know it's a variable squared minus 1, basically. So that trig identity is a secant squared minus 1. So I'm going to work with the secant. Whoops. Secant squared minus 1 is what I'm going to go for. Well, but here's the deal. If I want this to eventually be a secant squared, actually, I really want that to be a 4 secant squared so I can factor out this 4. So what I'm going to do is I'm going to rewrite my integral down here so it's in our visual field. Square root of 25 x squared minus 4 all over. I have to zoom up to see what it was. X. Secant of a fraction. Exactly. Well, it's a fraction times a secant. But yeah. So in this case, I'm going to say let x equal. Now let's go ahead and start building it. I need to get rid of that 25. So I'm going to divide by. Now you may say divide by 25, but remember, you're going to square what's going to happen here. So I'm going to actually divide by 5. That way, when I square it, it becomes a 25 and I'll divide off that 25. I also want to include a number so that when I square it, it becomes a 4. Now, what's beautiful about this substitution is you can quickly check, because you have to actually. X squared is 4/25 secant squared. Double check. If you let x squared equal 4/25 secant squared, well, just imagine with me, if this was a 4/25 and a secant squared, you see the 25s would cancel and you have 4 secant squared minus 4. So it does work out very nicely. Just bringing back everything that I had there. And so let's go ahead and use that substitution. Giving you a heads up, a lot of people will prefer to do the substitution slightly differently. I'll show you the substitution that they like to do after we're done. So this, I still need to trade out because I'm trading into the world of thetas. So I will go ahead and figure out what dx is. Dx is 2/5 times the derivative of the secant, which is the secant of theta tangent of theta, d theta. Everything's ready to go. Now remember the work involved for the u sub. It was pretty gnarly, right? A lot of work there. Let's see what happens with this. This is the integral of, well, the x downstairs, I'll start with that, is going to be 2/5 secant of theta. Upstairs, we have the square root of 25 times x squared, but x squared is 4/25 secant squared of theta, and then minus 4. And dx introduces a whole bunch of other stuff, right? 2/5 secant of theta, tangent of theta, d theta. And a lot of people see trig subs initially and they just go, man, that just seems like really messy. But in reality, a lot of things clean up. For example, the 2/5 cancel beautifully. The secants cancel beautifully. That's kind of nice. The 25s cancel beautifully. I can factor the square root of 4 out to the front. And I'm left with the square root of secant squared of theta minus 1 times the tangent of theta d theta. Everything else is canceled. And secant squared of theta minus 1, that's tangent squared. So I'm just going to write that below it. That guy right there is tan squared of theta. And we're going to take its square root. So that's going to be 2 times the square root of tan squared, which is a tangent, times tangent I didn't want to do that all in one step because I wanted to make sure I didn't lose anybody on that. So we have 2 times the integral of tan squared of theta d theta. A lot of people look at this and they go, I don't know the antiderivative of tan squared. You don't, actually. But you do know that tangent squared is secant squared minus 1. And you happen to know the antiderivative of secant squared is the tangent. This is 2 times the tangent of theta minus theta plus c. Now, as far as integrations go, that's actually a little cleaner than the u substitution up above. In fact, quite a bit cleaner. But unfortunately, we're ending in the world of theta, and we need to end in the world of x. So following the steps that I wrote down on the previous page, after you've done all that, the secant, isn't it tan cubed? No, it's not tan cubed. Because you took the square root of tangent squared, became a regular old tangent. Tangent times tangent is tangent squared, right? So at this point, we need to go back to our original substitution and draw a triangle for that. So my substitution here was that x is equal to 2/5 secant, or in other words, 5x over 2 is equal to the secant of theta. And if you want to draw that in terms of the cosine, you can. I'm actually not going to now. I'm just going to go ahead and draw a triangle. And it's supposed to be a right triangle. Sorry that it's not beautiful here. Secant is hypotenuse over adjacent. So now using the Pythagorean theorem, I can go ahead and say this is 25x squared minus 4. And now I can figure out what the tangent of theta is. Tangent is opposite over adjacent. So this is going to be twice. Opposite over adjacent is square root of 25x squared minus 4 over 2. And then here's the oddball, minus theta. So there are a bunch of ways you can write this answer. However, I'm just going to do it this way. Let me preface this by saying I do not like to work with the secant inverse, the cosecant inverse, or the cotangent inverse. I dislike working with any of those. So instead, I'll go ahead and flip both sides of this to say cosine of theta is equal to 2 over 5x. And now I can solve this for theta by saying theta, therefore, must equal cosine inverse of 2 over 5x. So if I do have a theta by itself, if I have a theta, not a tangent of theta, but a theta by itself, this guy right here. If a theta by itself in my answer, I can replace that with the cosine inverse of 2 over 5x. That's what I'm going to do. Cosine inverse of 2 over 5x. And then finally, plus c at the end. Obviously, you can distribute the 2 into this, and you would get, I'll go ahead and just magically distribute. Distribute the 2 through, and you get that. Okay. Now you may say, but wait a second. That's different than the answer we got up above. The answer we got up above, just at the top of your screen there, was the square root of 25x squared minus 4 minus twice the tan inverse. Well, if you want to write it in tan inverse, you can. It's totally doable. You can see right here, the tangent of theta is root 25x squared minus 4 over 2. So the tan inverse of root 25x squared minus 4 divided by 2 must be theta. So you could write it both ways. There's a bunch of different ways you can do it, but I just prefer the one using the substitution we used. That's just my preference. But you'd be right to use tan inverse or sine inverse as well. I try to avoid secant inverse and cosecant inverse and cotangent inverse because they're ill-defined functions. In other words, we don't use them enough to really warrant wanting to use them within an answer. So a very robust example because it showcases, again, old methods that you could use subs, or new methods that actually are a little speedier and cleaner, honestly. And these new methods end up being the only methods you can use at certain points. If you have questions anywhere in there, please ask. And I hope that, Raj, I answered why it's not tangent cubed. It's not tangent cubed because we took the square root of that tangent squared, right? And so that would be tangent times tangent. All right. So I'm going to hop forward. Yeah, no problem. Hop forward a page. Let's see. Time to move away from that secant sub. Let's move into something else. Here is an integral that looks to be something that maybe a u sub will work for, and actually a u sub will work here. But rather than trying to u sub first, let's just go ahead and dive right into the trig sub, since that's where we're at. So in this case, notice we're going to start by identifying what kind of substitution. It's some variable squared plus 1. When I see that, I immediately think, that's like a tangent squared of theta plus 1. That's the trig Pythagorean identity. So that's the substitution I'm going to use. Let x equal something like the tangent. But I need to include a coefficient so that when I square it, it'll be 9 times tangent squared. So I'm going to include 3. Now, I did say in the previous, I just recalled, I did say in the previous problem that there's a different way people like to do their substitutions, and I was going to show you. So let me go ahead and show you both in the previous example and this one. I'll start with this one. Another way you could have made this substitution is you could have said, you know what I'm going to do? I'm going to let x squared equal 9 tangent squared. A lot of people like this version because you're directly saying what you want x squared to be. I want x squared to be 9 tangent squared. And that tells you that x will be 3 tan of theta. And that's perfectly fine. That's actually a very doable substitution here. So you can do that. My only kind of argument against it is normally when you take the square root of both sides, you get an absolute value or a plus or minus there. And so there's a kind of a longer conversation to describe why there's no plus or minus. But that plus or minus is actually built into the tangent function. That's why there's no plus or minus. It's because the plus or minus has been folded in to the tangent, because the tangent can be negative or positive. So it's just a heads up as to why I didn't bother writing the plus or minus when I took the square root of both sides. But some people really like that style of substitution. They just say, oh, you know what I want x squared to be? Something like a tangent squared. Oh, basically a 9 tangent squared. Okay, well then do it. Take the square root of both sides. And normally you'd have the plus or minus, but because you still have an unknown right here, that tangent could be positive or negative. So I'm just going to fold that plus or minus into the tangent for now. That's all. You could have done that same substitution or style of substitution back here. So in this case, you would have said, you know what I want? I want that 25x squared to be 4 secant squared. Now, when people start seeing this, they're like, man, why didn't you do it that way the first time? Which I completely do understand that statement. Why didn't I do it that way the first time? It's just because I like to showcase the true substitution before I start going into these like, okay, but in reality, 25x squared, you're just letting be 4 secant squared. But then when you do that, 5x is equal to plus or minus 2 secant of theta. However, the secant of theta is going to be positive or negative, so that's just going to fold into that. So there we go. Okay. So from this point forward, I'm probably going to do my my x substitutions that way. That's just to give you a heads up. All right, going back here though, we now know x is 3 tangent of theta, and x squared is 9 tangent squared of theta. There's actually an x cubed up here we'll deal with in a moment. But let's figure out what dx is. Dx is 3 secant squared of theta d theta. And now we'll go ahead and plug everything in, basically. So this integral is going to be x cubed. So I'll just look at this guy and cube it. That'll be a 27 tangent cubed of theta. The dx we traded out for a 3 secant squared of theta d theta. And downstairs, we have the square root of x squared plus 9. That's going to be the square root of x squared is 9 tangent squared of theta plus 9. And now you just start cleaning things up. Actually, a very nice problem. Let's see. Factoring out the square root of 9, it becomes a 3. It'll cancel with the 3 upstairs. I still have a 27, though. Tan cubed of theta secant squared of theta d theta. And again, that was me taking this square root of 9 outside. It became a 3, but it cancels with the 3 upstairs. So that's why that's gone. And we'll have the square root of tangent squared. I was using my shorthand there. Tangent squared of theta plus 1, which, by the way, that tangent squared of theta plus 1 is, by design, a secant squared. And the square root of secant squared is secant. So this is now going to be 27 integral tan cubed of theta secant squared of theta over secant of theta. Taking my time. Normally you wouldn't have to do that, but just showcasing the steps here. And obviously a power of secant downstairs cancels with a power of secant upstairs. And so you have 27 integral tan cubed of theta secant of theta d theta. That is actually a much easier integral to deal with, believe it or not. But you have to be very creative with your variables at this point. If you take a look at that, we started with the integral of x cubed over the square root of x squared plus 9. We ended with 27 integral tan cubed secant. This goes back to the previous section, which are trig integrals, and we're going to do a u sub here. So you often have to do several techniques when integrating. The u sub you're going to choose here is not u equals tangent, because it'd have to steal away secant squared, but instead u equals secant, because if you let u equal secant of theta, its derivative will steal away a power of secant and a power of tangent, leaving the tangent with an even power, which is what I want. So this is going to equal 27. The secant and a power of tangent is stolen away. Secant, a power of tangent, and d theta, actually. So this, and a single power of tangent gets stolen away for a du. We're left with a tangent squared of theta. And we're back to the previous problem. That is 1 minus secant, or secant squared minus 1. Notice these are two different variables, but luckily we know what secant is. Secant is u. So this is 27 integral of u squared minus 1 du. And now you can integrate 27 1/3 u cubed minus u plus c. And then you have to go through all the resubs here. We have 2 of them. So u is equal to the secant. Let's just go ahead and start there. So this is going to be, I'm going to distribute the 27 as well. So 9, we get secant cubed of theta minus 27 secant of theta. That's what u was equal to, is the secant, I think. Yeah. And then you get to here, and you have to realize your original problem was not even in the world of thetas. It was actually in the world of x's. So you'll have to go back and figure out what theta is in terms of x, or basically draw a triangle for your original substitution. So we know that x over 3 is the tangent of theta. So drawing a picture, here's theta. I always draw my pictures in quadrant 1. Please do not judge me on that. It turns out that drawing your pictures as a quadrant 1 triangle does not hurt. So we'll go ahead and just do that. Opposite over adjacent. And the hypotenuse would be x squared plus 9 square root. Which, by the way, you'll notice very often that radical component is almost always in our answer. And we want to know, what is the secant of theta? Well, secant of theta is hypotenuse over adjacent, root x squared plus 9 over 3. So this is going to be 9 times something cubed, which is root x squared plus 9 over 3, minus 27 times root x squared plus 9 over 3. Obviously, this is going to simplify. Let's see. 3 cubed is 27. 9 goes in 27 3 times. So it's 1/3 times the quantity x squared plus 9 to the 3 halves minus 9 times, I'll just write it as x squared plus 9 to the 1/2 plus c. A very, very robust problem again. Just letting you know, they all kind of work like this. They look nasty and they look like they take a while, but practice makes better with these. You start working with these and realize they're not bad. They're actually kind of entertaining. It's really good practice for all of your trig identities. Take a drink real quick. All right. So we've seen 2 of them so far, right? We've seen the secant substitution and the tangent substitution. We have not seen the most popular substitution. How would we know to look at this problem and think trig sub, right? Yeah. Generally speaking, if I looked at this problem, I'd probably think u sub, honestly, first, because I think a u sub would work beautifully here. However, if you try a u sub and it doesn't work, then, and I usually only spend about maybe 2 minutes trying to work through an integration technique. And if my integration technique after a couple minutes of work seems to not be working, I will press pause on that and I'll switch gears. And in this case, I would say, well, that is a sum of squares downstairs. It's something squared plus something. So I think that'll be a trig sub. If it's a sum or a difference of squares, basically, that's a good way to think. Trig sub is a possibility. It's not a requirement. There are other ways to do this, but it is a possibility. Yeah. I'll leave it to you to try this as a u sub. I think it will work. It will work, actually. It will totally work. And it's actually a much easier problem as a u sub. Much, much easier now that I'm thinking about it. But let's go ahead and try yet another example. Is this the one? Yes, this is the one. Okay. This will round out the day with the most popular style of, I say the most popular style because this is the one that 50% of the problems in trig substitution homework usually consist of this style, where it's a difference of squares, but it's a number squared minus a variable squared. When I see that, I think 1 minus sine squared. This also brings up an alternate conversation. People say, well, why can't I call that 1 minus cosine squared? You totally could. The problem is, remember, if you let x equal, something like a cosine, dx will be a negative number. And that extra little addition of a negative into the problem, it's a possibility for an error. So we tend to do on this a sine substitution. It's like a 1 minus a sine squared. So in this case, that's where I've identified. I could try a U sub, but it's not going to work. I'll just promise you that right now. So I will go ahead and say, let x squared equal, because I'm going to do what I did in the last problem where I'm not going to let x equal, but this time I'm just going to say, you know what I want x squared to be? 9 sine squared. And that implies that x is 3 sine of theta. Yes, it would be plus or minus, but again, sine of theta, that we don't know what quadrant theta is in. It's either in 1 or 4, but we don't know which of those two quadrants. So that's where the plus or minus comes into play. So it's going to be folded into the sine, basically. And this allows us to figure out what dx is, which is 3 cosine of theta d theta. And again, this is why I do a sine substitution right here rather than a cosine substitution, because dx would be negative if you did a cosine substitution, and I don't want to deal with that. We have everything we need. This actually happens kind of quickly, I think. Let's see, dx, we're going to steal that away for a 3 cosine of theta d theta. X squared, well, that's 9 sine squared of theta. And then we have the square root of 9 minus x squared, which again was a 9 sine squared of theta. We have transferred into the world of thetas completely. I know 3 goes into 9 3 times, so I'll at least write that 1/3 out front. And you should probably now really be pretty quick at seeing square root of 9 pulls out. That's going to give us another 3 downstairs. And that's a 1 minus sine squared, which is a square root of cosine squared, which is a cosine. Okay, let me say that again. This is basically after you move the 9 out, it's a 1 minus sine squared, which is a cosine squared. But you're taking the square root, so it's a cosine. And normally it'd be the absolute value, but there's something very special that I'll put in a different video. The cosines cancel. And here's a funny little integral. 1/9, integral of 1 over sine squared. Whoops. Secant. D theta. I say it's a funny little integral because I will have people that get stuck right here when they shouldn't. 1 over sine squared is the cosecant squared. Always try to do your trig before anything else. And if you think, oh, I have 1 over sine squared, how do I integrate that? It's probably easier to think, oh, wait, 1 over sine squared is cosecant squared. I happen to know the antiderivative of cosecant squared, right? So the antiderivative of cosecant squared is the negative cotangent. Because again, derivative of the cotangent would be a negative cosecant squared, but unfortunately that negative wasn't there, so there you go. Now, pretty clean. All we need to do is go back to our original substitution, this guy right here, and draw a triangle. X over 3 is the sine of theta. So I know that if I draw a triangle, and if I call that theta, then the opposite is x, the hypotenuse is 3, and the adjacent is the square root of 9 minus x squared by the Pythagorean theorem. And now I can read off of this the cotangent. Cotangent is adjacent over hypotenuse, root 9 minus x squared over x. So negative root 9 minus x squared over x, which has a 9 attached to it. There you go. Super clean method. Again, once you start doing these, I think most people actually fall in love with them. They think that this is the end all be all. I'm going to totally do all my integrals using trig substitution. Don't. As I said a few minutes ago when I was doing the previous example, that that example could be done much, much faster using a U sub. This problem can't. This problem you can only use a trig sub on. But the previous problem, this guy right here, a U sub to me looks to be a much faster technique. And you guys are so early in your integration careers that you may not see it. But now that we finished that previous example, I just want to showcase the U sub in this one. So I'm going to do that all in blue so that you can see it's x cubed over the square root of x squared plus 9 dx. And watch how quick it is. If I let u squared equal x squared plus 9. Now, that might confuse you. So let me just say, I let u equal the square root, and then I squared both sides, okay? So if I let u equal the square root, so that u squared is equal to x squared plus 9, then 2u du is equal to 2x dx. Obviously, the 2's cancel. So I get to steal away a power of x and the dx upstairs and trade them out for a u du. So I'm left with x squared u du. Downstairs, that picture is u. So the integral of x squared du. But what is x squared? It's u squared minus 9. Oops, du. And that would be 1/3 u cubed minus 9u plus c. And now I'll substitute back in what u was. U was the square root of x squared plus 9. So this will be 1/3 x squared plus 9 to the 3/2 minus 9 times x squared plus 9 to the 1/2 plus c. Now compare that amount of work to what we did. So this is why I'm saying people love trig subs, but it is a dangerous substitution because it can lead to long solutions. Whereas if you can see a U sub, do it. U subs are super nice. So didn't expect that to happen, did you? That's a really cool U sub. I dig that U substitution. So questions on so far trig subs. You do have to memorize the tactics here. It is totally memorizable. You do have to have those in your back pocket ready to go at any given moment. The only thing that we haven't really talked about, actually, we've talked about every style here, but you could see on Monday, what we're going to go through would be now definite integrals. And this looks terrible, but with trig subs, things don't remain terrible for long, actually. Things clean up beautifully. But there's one. This is what we're really going to focus in on. Just giving you a heads up, think complete the square. And then same thing here, think complete the square. So these are where we're ending Monday with. So I think that's a pretty good place to stop for today, even though we're 3 minutes early, but I've kept you late a couple times. So I figure today's a good day to stop a little bit early. I have office hours in 12 minutes. And remember, you have a quiz today, so you can log in anytime between 10 and 9 p.m. to start taking the quiz. It's a single question. Before you hop out, let me just give you some information so that I give you, so you can manage your daytime easily so that you know how much time you'll need. So it's a quiz on 7-1, and let me get on my student view so I can actually see questions. Oh, it should be very short, actually. Settings, time. I give you 10 minutes. It's a super short problem. 10 minutes. So just reserve 10 minutes of your time today to log in and do that after 10 a.m. And I'll see you there. Otherwise, I'll see you in about 12 minutes for office hours. And you guys have a wonderful weekend if I don't see you. And I'll see you on Monday. And I'll record that video. The video for the justification for not needing the absolute values. All right. I'm going to step away for a few moments. I'll be back.